Hello and welcome to Lecture 3 Part B of Chemistry for the Interdisciplinary Sciences. Today we're going to keep talking about our ionic reactions. Let's have a quick look at the learning outcomes. We're going to take this opportunity to start thinking about some terminology, especially compound, mixture and element. So we're going to define those a couple of times and have a think about them. We're going to define the term ion again and just predict the likely charges that we're going to see on an element, though we have sort of done that in the last lecture too. I'm going to remind you to learn the names of the common ions, really important, and again I'll remind you of those rules really quickly. And then we're going to have a look at displacement reactions. So that's where we use the reactivity series to find out if some metals are going to force other metals out of a solution. Finally, we're going to note again that when a reaction happens, we've got to think about how many atoms of each type of donating electrons and gaining electrons, or metal and non-metal, that we have in there. And it's got to be even. It's got to be the right number of electrons to transfer over. So let's just start by reminding ourselves about this terminology here. We've said element quite a few times. What I mean by that is a substance that is made up of only one type of atom. And when I say one type of atom, I mean one atom that always has the same number of protons. Might have different numbers of neutrons, but it only has one type of atom with one number of protons, whatever that is. So for instance, if that's iron, then all the atoms in a block of iron that is a pure elemental iron will all have the same number of protons. And if we have a quick look at the periodic table, it's 26. So it's going to have, every single atom will have 26 protons. They're all going to behave exactly the same. When a substance is made of just one type of atom, like iron or a helium balloon or some iodine that you rub on, essentially any element, pick an element, they're all the same. That would just be an element. And we would write them with just their elemental symbols. So if I were to write iron, I'd just write Fe, He for helium, I for iodine, and that's it. When a substance is a little bit more complex, it's still all bonded together, but now we've got different types of atoms coming together. So that's things like water, H2O, you've probably heard that before. That's two hydrogen atoms and one oxygen atom physically bonded together into a single substance, a single molecule of its own. This is a compound. Every single molecule in that selection, so for instance, my salt from the last time, every single molecule in here is made of sodium and chloride put together. It's just that there are two different types of atoms in there. There's not also some random other things like iodine or whatever in there. They're all sodium chloride, but there are two different types of atom in this substance, or there is more than one. So that defines a compound. Water is our quintessential example, sodium chloride, but it can get more complicated. Sucrose, which is the sugar that goes in your tea, is C12H22O11. What that means is 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, and the exact structure of that substance defines it as a certain thing. Finally, we then come to mixtures. What if in this salt, and if it was proper, it's lovely sea salt. If it's sea salt, it also has a little bit of potassium iodide in there as well, and that's where we come to a mixture. So this is a mixture of sodium chloride and a little bit of potassium iodide, and that's what makes sea salt taste different to table salt or rock salt for that matter. Rock salt also has some different compounds mixed in. So a mixture might be cola, for instance. Cola, if you read cola's ingredients list, it is literally water, sugar, and brown colouring, and that's what that is. But it's a mixture. If I water down my cola, if I add a few ice cubes and they melt over time, I've still got cola, and so the ratio of the substances does not define that substance. Whereas before, water, H2O, it has to have two hydrogens, it has to have two oxygens. Two hydrogens for every one oxygen. That's it. No other structure is water, is that compound. With a mixture, it can be all sorts of different things. Soil is similar. It's got, silica in there, sand, I mean by that, celluloses, it's got bacteria and so on in there as well. It's got nitrates in there. So soil is a mixture of things, and again, you can get different types of soil. You can get sandy soil or dry soil or acidic soil. All that must be a mixture then. And then something like brass or steel. Steel is a mixture of iron and some other metals sometimes, or other elements like carbon. Usually it has to have iron and carbon in, but they might also have nickel in there or something like that. that too is a mixture. The brass can be, steel can be high carbon or low carbon. So there's not one defined mixture that is steel. Steel is a mixture of iron and carbon in some ratio or other, and some other elements. So that would be the definition of those. So I'm just going to go through a few of these and have a look. So here we've got, again, that reaction that we saw in the last section. Iron and sulfur make iron sulfide. In this case, we have an element, iron. Iron is an element because there's only one elemental symbol in that substance. Sulfur is the same, only an S. And then in this, we've got a compound. We've got iron and sulfur together. So I want you to have a little go yourself. I want you to look at these and have a pause and think, is this an element, a compound, or a mixture? So mercury. Is that an element, a compound, or mixture, and how can you tell? So the answer is that mercury appears on the periodic table all on its own. So where is mercury? Right at the bottom of the D block on the right-hand side, just before it becomes the P block. Proton number 80 is mercury there. So mercury appearing on the periodic table, and this not being a mixture of anything, mercury is an element then. So A is the correct answer for this one. It's an element. How about carbon dioxide? So carbon dioxide, a carbon and 2 oxygen atoms. This is a compound then. I've got 2 different elements in there. It's not just carbon, it's carbon and oxygen. So this one is C, a compound. Liquid nitrogen. So again, nitrogen appears on the periodic table. It's on the second row, let's pop up, second row, group 5 there, nitrogen on its own. Just because it's a liquid doesn't change the fact that it's an element, and so liquid nitrogen would be an element all on its own. It's just made of nitrogen. Hopefully I'll show you an experiment later on with that. How about the air? What is that? Great, so you might not know a lot about the air, that's fair, but you do know that the air contains oxygen because you breathe it perhaps, and you might also know that the air contains water because we can see the clouds there. So we know that there are at least 2 different separate substances in there, and that means that the air is a mixture. The air is mostly made of nitrogen as well, so it's different to the liquid nitrogen in that it's, nitrogen and oxygen and argon, water, carbon dioxide and so on. So that's a mixture. B is the correct answer there. It's a mixture. Finally, sodium chloride. Lovely. So you might now have gathered that it's a compound. It's got 2 different elemental symbols in there. We've got sodium and chlorine. So it's a compound. And you might even be able to go further and say what type of compound it is. It's an ionic compound. Why is it an ionic compound? Because it contains sodium, which is a metal, and chlorine, which is a non-metal. So that being the case, what we've got there is a compound. So C is the correct answer there. So we're going to carry on talking a little bit more about ionic bonding today, and that does require me just to go through and summarise a couple of extra points. So I'm just going to very quickly remind you of the definition of metal and non-metal. A metal is something that's going to lose electrons in order to get to a stable full shell electronic configuration, or full orbital or half full orbital. And a non-metal is doing the opposite, it's gaining electrons in order to do that. And so the metals tend to be on the left-hand side of carbon, the non-metals tend to be on the right-hand side of carbon on the periodic table. Now, transition metals are really interesting because the transition metals tend to make coloured salts. So you can see in the middle here, I've got sodium chloride. Sodium is not a transition metal, so we go to the periodic table. Sodium is over there in the S block, and transition metals are all the metals in the D block there in the middle. So we got iron chloride, we got nickel sulfate, copper sulfate over here, that lovely blue colour, and cobalt nitrate. Metals, salts made of transition metals and with partially filled d orbitals tend to form those coloured salts in there. The reason for that is to do with the electronic energy levels that we saw before. You remember we talked about transitioning in between the different energy levels. When you've got a partially filled d orbital, it can transition in between nearby occupied or unoccupied electronic energy levels, and it can do that using only visible light. So you remember before we were using a flame to do all that promotion, demotion. With a transition metal, the d orbitals are so close to all the other nearby orbitals that it can just do that promotion and demotion using just normal visible light. And that's what makes up a large majority of the coloured compounds that we see. Behind me is a green screen. That green screen contains a compound probably made of transition metals in order to be green. And you'll be aware of chlorophyll, for instance, in nature there. That is the compound that makes leaves green as well. It contains iron in there. So that too is a transition metal. So I've mentioned, I just want to clarify and make clear that I don't expect you to do any electronic configurations after krypton in this one. So you don't have to go past the 4p orbital there. That's all you need to be able to do. And I also want to remind you that the 4s fills before the 3d, and that's why the top row of the periodic table in the D block there, we call that the 3d energy level. So I do want you to remember that 4s fills first. So we mentioned this idea that ions form, and an ion, again, is an atom that has a charge on it. Ions form in order to satisfy the favourable electronic configurations, full shell, full shell, full orbital, half full orbital. I've said that thousands of times now. And they do that to obey what we call the octet rule. It's a silly name for a rule because not all of the shells contain 8 electrons. In fact, only 2 of them do. But we call it the octet rule. That just means filling up the shell that we're talking about before. So I mentioned this idea that I'd like you to be able to look at the periodic table and decide what charge an ion is going to have, especially if it's in the S and P blocks. Remember, for the D block, it can be quite variable. I'd like you to be able to make an argument one way or another as to what you think it's going to do, but definitely for the S and the P elements, you want to be able to say, oh, it needs to lose 2 electrons, or it needs to gain 4, or whatever that is. So the example here that I'm giving you is magnesium. Magnesium on the periodic table is in group 2. Down there on the 3rd period, so that's proton number 12. Magnesium, being in the 2nd group, has 2 electrons in its outer shell. It wants to lose those electrons because losing 2 is easier than gaining 6 and getting over there to the full shell. And so it will form 2 plus ions. It's really important that you're able to do the bit where it's plus or minus. Am I losing electrons and making it positive? Or am I gaining electrons and becoming more negative in that process? Now, you might hopefully have seen the worksheet for the workshop last week. I would like you to remember that the 4s fills before the 3d. Now, anyone who's studied chemistry before might be aware of another rule, which is that the 4s empties before the 3d. I'd like you to be aware of it, but it's not going to be examinable in this course. So be aware that that is not something that we're going to have to do. So don't worry about that, but you might as well know that that is the case. The 4 empties first because the 4 is actually a further away shell than the 3, despite the fact that the 4 fills first for energetic reasons. So that's what's going on there. Okay, lovely. And finally, we just have to talk about one more really interesting compound, because we're gonna see it quite a lot and think about it a lot. Hydrogen, having only 1 electron and being in a shell that contains 2 electrons, can either gain electrons and have 2, or it can lose electrons and become positively charged and have no electrons, which we count as being a full shell as well. That also seems to be stable. So hydrogen's a really interesting one that's sort of sat there in the middle, and it can do either. And carbon is sort of the same, carbon, silicon, and so on. Those compounds also can gain or lose because they're in the middle of the periodic table, like both ways are a long distance to go. So just be aware that hydrogen can form H plus ions or H minus ions, and that's what makes it so interesting for something that we're going to look at later on. That's not what I wanted to click. One other thing. So it is the case that if you can take an electronic configuration to do with the d orbitals and rearrange those electrons into a way that satisfies those three rules we were talking about before, then you should do. And again, if you've studied chemistry before, you might be aware of this. So for copper, let's have a quick look at the periodic table again. Copper is right near the end there of the very first row of the D block, proton number 29. We would say it's 4s2 3d9, wouldn't we? It's in the 9th position. However, if we rearrange those electrons, instead of being 4s2 3d9, we promote one electron from the s to the d, which is not a very large energetic difference, then it could be 4s1 3d10, and that is more stable than 4s2 3d9, because now you don't have a d9 configuration, which is unfavourable because it's neither a full shell, a full orbital, or a half full orbital. Whereas in this case, 4s1 3d10 contains a full orbital and a half full orbital, which are both stable. So it is the case that happens. I'm not going to examine you on it, but most A-level syllabi will mention that and say that it's really important. It is important, but we have a lot to learn this year, so let's not worry about that too much. But just be aware again that we have those three conditions that electron configurations are trying to get to. And the same is true for chromium. Again, if we have a look at the periodic table, chromium is in position 6 along there. Oh, position 4, sorry. So 1, 2, 3, 4 along on the D block, it must have 3d4 electronic configuration, so 4s2 3d4. If instead of being 4s2 3d4 we promote one electron up, then we can have 4s1 3d5, and that too is more stable than the other configuration. Just worth knowing, I'm just pointing it out. Again, this is not an examinable material, but I'm mentioning it because it's interesting. Lovely. And then finally we're going to mention the strength of the ionic lattices again. So I asked you to learn these common ionic compounds. Again, I'm reminding you that if it's just the element with a negative charge, it's "ide", and if it is one of these complicated ones that have oxygens in, they have slightly different names. So we've got hydroxide, and then basically the element with an 8 at the end of it's got oxygens in. And the number of oxygens might look a little bit weird at the moment, but eventually we're going to learn how we can predict that later on. So finally, we come to the ionic reactions that we want to talk about today. We've got precipitation reactions that we saw the last time. That is when the ions go in unchanged and they just swap partners. So the lead is still the same charge it was before, the iodide is still the same charge it was before. There's been no transfer of electrons, they've just swapped ionic partners. The pluses and minuses have swapped around which positive ion, which negative ion that they're attracted to. In the next reaction that we're going to look at, we're going to look at the reactivity series. So we're going to look at a displacement reaction. Now, the reactivity series talks about the nature of metals. By definition, a metal is something that loses electrons, that removes electrons, and so there must be such a thing as a strong metal and a weak metal, an atom that really wants to lose electrons and an atom that really wants to gain, that hardly wants to lose electrons. By definition, if it's a metal, it can't want to gain electrons. So here what we've got is a reactivity series. We've got platinum, gold, silver, copper down at the bottom. Those things hardly react at all. And when they do, they lose electrons, but they hardly ever do that reaction. And then we've got things like potassium, sodium, and so on that we saw in that very, very first lecture where they went into the water and they immediately reacted. They're really reactive. And so some metals are better metals than others. They are more willing to lose electrons and force electrons onto the other compounds. And so what will happen is more reactive metals will force their electrons onto ions that are less reactive than them. Now, you will be given a reactivity series in an examination situation, so you don't have to remember what this is, but we can have a very quick look at the periodic table and see if it makes sense. So I said that gold, silver and copper are not very reactive, and if you look at where they are, they're there in the D9 position. So again, we're looking at copper at the end of the D block on the first row. We've got silver and gold. Those are all very stable. They don't want to change because of that thing I was just talking about, where it's 4s1 3d10. All of them can have 3d10 configurations, and so, you know, they're happy enough, they're fine. But if we look at sodium, lithium, potassium in group 1, all of those only have to lose one electron to have a stable electronic configuration, and so they will, as quickly as they can, with whatever they can, they will force their electrons onto something. So in a reactivity series like this, a displacement reaction is where an elemental metal, like zinc for instance, being more reactive than copper, forces copper to go back into its metallic state, and thus zinc loses its electrons and becomes ionic. So what's going to happen is it's going to switch through into zinc being the one that's ionic and copper being the one that's solid. Now, the reason it becomes solid is because it's uncharged. And being uncharged, it means it doesn't want to interact with the water. It is itself a metal. It wants to bond with other metal atoms in there. And so what we will see is that they will have a lowercase s. So we're starting to look at what we call phase symbols. Word completely left my head there for a second. So we got elemental zinc. It's a metal and it's a solid. We have copper, the ionic copper. Now in this case it's going to be in a solution, and so we say it's aqueous, aqua being water, we say it's in water itself. And so for numbers 3 and 4 you can imagine that it's going to become the opposite. The zinc is going to be the one that becomes aqueous, that goes into solution, and the copper is going to be the one that becomes a solid. So when they're written on their own, they tend to be dissolved in water, especially when they're doing a reaction. Otherwise, they'd have to be a solid salt, in that lattice that we talked about in the last section. So there's no such thing as a source of a positive ion. What I mean by that is, in that last reaction, I can't just put copper 2 plus ions into something. They have to come with something called a counter ion, the other part of that substance, if you want. And so, for instance, this might be copper sulfate. Sulfate was one of the ions on the list, and it's a negative ion, so it can bond together with a positive ion. And when we have transition metals that have those variable electronic configurations, we tend to say exactly what the charge on the metal is in the name. So you can see here, what I've written is copper 2 sulfate. That means that the copper must be in the 2 plus charge in that compound. And we call that an oxidation state. I'm going to define that way later on. But for now, copper 2 plus is defined by the fact that there's the 2 in the name there. And again, we only have to say it when there's elements of variable charge. We don't need to say lithium 1 chloride, because lithium is always going to lose 1 electron because of its position on the periodic table. They're in group 1. So we only need to do that when there's elements with variable charge, and that's largely going to be our transition metals there. So let's imagine then that we must have some counter ion in this solution. We've got zinc and copper and sulfate, so that's copper sulfate in there. And at the end, what's going to happen is the zinc is going to go into solution, force its electrons onto the copper, force the copper out of solution, and notice that the sulfate has just hung around. Nothing's really changed before or after. We call this a spectator ion. It means that it's done nothing. And so we can basically ignore it in our solution, and that takes us back to that original formula that we wrote in the last couple of slides. So displacement is when a more reactive metal is added to an ionic compound in order to force its electrons onto that less reactive metal. And we're just going to have a very quick look at the electronic configurations to figure out what's going on. So elemental zinc has that 4s2 3d10 configuration, but we've got some electrons in the 4th shell there that we'd rather not have. So zinc is going to get rid of those 2 electrons in that 4th shell, and therefore have a relatively full electronic configuration. It's got a full 3 shell there, which is great. Copper, on the other hand, even in solution here, is 3d9. That's not a full orbital or a half full orbital or anything like that. So by accepting electrons, it actually goes to a 4s1 3d10 configuration again, which is more favourable than what it was in solution in the first place. Again, this is what makes copper unreactive, really. So let's have a quick look at this reaction. Here it is. It's a beautiful chemical reaction. We'll have a look at quite a few, actually, and we'll see what's happening. So these are displacement reactions. So here what we've got is zinc displacing silver. Silver is an unreactive metal, and what's growing are the silver metals themselves. You can see they're growing these beautiful little trees. This is silver coming out of solution, being dissolved and becoming a solid. So here's our zinc and copper solution. You can see the zinc there is the solid bar on the inside, and can you see how the skin of the zinc is sort of sloughing off that substance there? The top of it is going to be zinc oxide, and then under it we're going to have our zinc. Let's keep having a look at that. So there, what we should be seeing there is the zinc under that oxide layer being eaten away and dissolving into the solution, and the copper will be deposited on top of that skin probably, and that makes it even heavier to go down. Let's have a look at a couple of others. So here we've got zinc and lead. Lead is also quite unreactive. It's in group 4. It's not going to get to a good stable electronic configuration. And so again, lead comes out and grows these lovely little trees. That's because again, the metals are just forming that little sort of lattice shape there. Is there another one? No, that's the end of it. Oh, some precipitations. Let's have a look at those precipitation reactions anyway, because we looked at one of those last time, didn't we? So here in a precipitation reaction, what's happening is ionic partners are swapping. We're not having elements change from solids to... Yeah, we're not having elements losing electrons in this process and other elements gaining them. Instead, we're just seeing ionic partners swapping. So that's what's going on there. We've got a silver there swapping its partner with the bisulfite to make a silver sort of sulfide-y thing, and sodium nitrate in there. Let's just watch one more of these reactions because they look really nice. Ooh, a chromate reaction. So the chromates are really nice colours. You can see it's going orange to green there. The chromium in that compound, it's a really nice place to stop. The chromium is in the top row of the D block there. It's a transition metal. So being a transition metal, it has variable oxidation states. And that's what we see in this reaction. We can see it starts off being in a certain oxidation state, having a certain charge. It starts off orange, and then it slowly probably reacts with the oxygen inside the water there to make a sort of oxide of chromium there, which is that nice green colour. It's a really nice example there of what we've got going on. Lovely. That takes me to the end of this section about ionic reactions. Hopefully that makes sense. If it doesn't, please do feel free to get in contact with your tutor and ask any questions you've got, or turn up to workshops or book some office hours or something like that, just to give it a go. And also you should find some tutor notes in the folders that you found these videos. See you at the next one.